You know, if you've ever watched a military jet streak across the sky, you've definitely seen it. That dramatic, roaring cone of fire just trailing right out of the tailpipe. But here's the thing, that flame isn't just for show. Not at all. It actually represents a raw, brutal manipulation of physics that's specifically designed to keep a pilot alive in the sky. Today, we're going to completely demystify this. We're going to figure out exactly what that fire is, how it works, and why it is absolutely critical for modern flight.
So right off the bat, I want you to ask yourself a question. What actually happens when you take raw, highly combustible jet fuel, dump it directly into an exhaust stream that is already scorching hot and just let it ignite? Well, the result is that intense cone of fire. In the world of aviation engineering, they don't call this a flamethrower, although it sure looks like one. It's called an afterburner, and it's a piece of technology that completely transforms how a jet performs in midair.
Okay, let's dive into this. Consider the sheer staggering temperatures involved here. When an afterburner kicks in, it triggers a secondary combustion event right inside the exhaust pipe of the aircraft. Because the exhaust from the main engine is already incredibly hot, the newly injected fuel ignites instantly. It literally doesn't even need a spark plug. This violent second explosion raises the temperature of the exhaust gas to a blinding 1700 to 2000 degrees Celsius. At those extreme temperatures, the expanding gases accelerate massively, and that is what creates that iconic visible flame.
So the crucial takeaway here is understanding what an afterburner fundamentally is. The British actually call it reheat, which is a pretty accurate name. It's a secondary combustion system, and it exploits a really brilliant trick. A standard jet engine only actually uses about 25% of the oxygen it ingests from the air to burn fuel in its main core. That means the other 75%, it flows right out the back as hot, oxygen-rich exhaust. The afterburner cleverly takes advantage of all that leftover oxygen by injecting even more fuel directly into it for a massive secondary explosion.
Let's break this down into the simple terms of Newton's third law, right? Pushing mass backward to go forward. In a normal jet engine operation, you compress the air, mix it with fuel, burn it, and expel it. That is steps 1 through 4, which creates what we call dry thrust. But the afterburner introduces what I like to call a thermodynamically crude but highly effective step 4B. Right before the exhaust leaves the nozzle, a ring of injectors just sprays more fuel into the jet pipe, and we burn that mixture all over again to squeeze out every absolute last ounce of push.
To truly appreciate this, we kind of have to look at the contrast between these two modes. Dry operation, which is known as military power, relies on the elegant, precise engineering of the main jet engine core. The fuel burns at perfectly controlled temperatures and pressures. But then you have wet operation, or maximum power. And with wet operation, elegance goes completely out the window. It is a brute force raw explosion. It totally lacks the sophistication of the main engine, but man, it makes up for it in sheer, unadulterated power.
And here is the jaw-dropping result of that brute force. Engaging the afterburner can provide an instant 40 to 70% boost in thrust. To put that into perspective, an F-16 engine can jump from 17,000 pounds of thrust to nearly 29,000 pounds in just a matter of seconds. It's literally the engineering equivalent of pure adrenaline being injected directly into the aircraft's veins. This is exactly the kind of power that violently shows a pilot back into their seat and shatters the sound barrier.
But making this work reliably, it's incredibly difficult. Dirk Filippona, an engineer at Pratt & Whitney, has this incredibly vivid analogy. He compares afterburner ignition to lighting a butane lighter when you're sticking it out the window of your car and holding it behind the side mirror. Think about that. You have air racing past at hundreds of feet per second. Trying to stabilize a flame inside a hurricane of high-velocity exhaust requires meticulously designed flame holders just to keep the fire from blowing itself out.
So why go through all this trouble? Well, because there are life or death scenarios where efficiency simply does not matter. Pilots absolutely need this raw power for short takeoffs from the incredibly tight decks of aircraft carriers. They need it for transonic acceleration, to violently punch through the aerodynamic drag of the sound barrier. They need it to maintain energy in high-G dogfights, where turning rapidly bleeds airspeed. And, most importantly, they need it for rapid missile evasion. In those critical seconds, survival is all about thrust. Section 1. The catch. The fuel economy problem. Now, what's really interesting about this is that, as with all things in physics, you don't get something for nothing. There is a massive thermodynamic trade-off required to tame this beast. Take the fuel consumption of an F-16, for instance. In standard dry mode, it burns a respectable 60 liters of fuel per minute, but the second that pilot kicks it into afterburner mode, that consumption skyrockets to 180 liters per minute. It roughly triples. This savage fuel penalty is exactly why most fighter jets can only sustain their afterburners for a few minutes before their fuel tanks completely run dry. It is an emergency reserve, for sure, not a cruising gear.
Section 2. A history of brute force. To understand how we ended up with this wildly inefficient system, we have to look back. The experimentation actually started back in 1941 with the Italian Caproni Campini N1. Then, by 1944, American researchers at NACA were testing early afterburners on the General Electric IA engine. But the real rapid evolution, that happened during the Cold War. In the 1950s, we saw mass production of afterburning jets like the American F-94 Starfire and the Soviet MiG-17F. And they had massive teething problems. Early alloys would literally melt under the extreme heat. Actually, fun fact, some early MiGs had to carry dedicated tanks of ethanol just for the afterburner, simply because standard jet fuel burned way too hot for their unrefined metals to handle. In early 1946 ground tests, like those done on the Ryan-designed afterburners, you can really get a sense of how crude yet brilliantly effective this all was. Engineers were essentially taking heavily reinforced pipes, bolting them onto the backs of early turbojets, spraying fuel inside, and measuring the chaotic results. It was pure trial and error, pushing the absolute limits of material science at the time.
Historical documentation from NASA and Ryan Aeronautical really highlights that this was fundamentally a crossbreeding exercise. Basically, they took the principles of a ramjet, which, if you don't know, is essentially a flying tube where air is compressed by forward speed alone and then ignited, and they bolted that concept onto the back of a standard turbojet engine. This mechanical cross-pollination laid the absolute foundation for every modern combat propulsion system flying today.
Section 3. The future of jet propulsion. But we are now entering the dawn of digital design, and the ultimate quest for modern aerospace engineers is to solve this fuel problem permanently. Enter the Adaptive Cycle Engine. Developed under the U.S. Air Force's Adaptive Engine Transition Program, or AETP, this is a revolutionary leap forward. Instead of forcing engineers to choose between an engine optimized for speed or an engine optimized for fuel efficiency, the Adaptive Cycle Engine automatically reconfigures itself in mid-flight. It gives pilots high thrust for combat when they need it and high efficiency for cruising when they don't. It is a complete paradigm shift from raw brute force to smart power.
Let's see how this builds into real-world hardware with the General Electric XA100 engine. The standout innovation here is this brilliant third-stream architecture. Traditional jet engines basically have two streams of air, but the XA100 introduces a third bypass stream. This provides a crucial extra source of cooled air, which allows for incredible thermal management and increased thrust. And best of all, it drastically reduces the need to rely on the traditional, highly wasteful, fiery afterburner. And this brilliantly illustrates the real-world impact. By replacing brute force with adaptive digital airflow, the XA100 delivers massive gains, a 25% improvement in fuel efficiency and a 10% increase in raw thrust. Plus, it provides a massive leap in thermal management. What this means is that next-generation fighters will be able to go significantly further, stay in the fight much longer, and power highly advanced electronics, all without guzzling fuel the way traditional afterburners do.
So, I'll leave you with this final, provocative thought. Is the era of the iconic fighter jet flame officially coming to an end? As we move into a future completely dominated by stealth requirements, supercruise capabilities, and digitally managed adaptive engines like the XA100, the need for that highly visible, fuel-chugging cone of fire might just fade away into aviation history. It is pretty incredible to think that the brute force afterburner that defined an entire century of air combat might soon be replaced by silent, invisible, smart power.
Don't forget to like and subscribe for more How Meets History.